Hi everyone. This talk is about various technical challenges we overcame while scaling our functional tests. My name's Tim Baverstock, and I've worked on test infrastructure at Magic Lab Badoo for just over 5 years. I was originally working on test tooling with all our supported platforms, iOS, Android, mobile web, and briefly Windows Mobile, but the tools team has grown, and now I'm mostly focused on Android. When I joined the company, we had 300 tests running on 5 or 6 Android phones at a time, taking 4 hours, and usually only running overnight, after everyone had pushed their changes to master and gone home. And these tests were viewed as an unreliable nuisance when developers came in each morning. Now we have 1,500 tests running on around 120 emulators at a time, taking 30 to 40 minutes. They run on developer branches before commit, both on demand and as part of the workflow, and developers seem to consider them useful. Most of you know us as Badoo, but we are part of the Magic Lab group that also developed the application Bumble. We have over 500 million users worldwide, which is something like a 16th of the world's population. So here's the outline. A couple of examples on how to reduce wasted test effort without spending money, then an account of how I moved our phone-based testing into Docker, including a patch to Adb, a rundown of how I build Adb from source to apply my patches, our attempts to run emulators in Docker along with more Adb patches, how I build snapshot containers with Docker, and some random problems we encountered with patches to fix them, some notes on selecting servers and calibrating them, an outline of how we're trialing Kubernetes, and a section on how we need to change our current setup to better allocate computing resources. When you climb a mountain, you don't head for the summit in a perfectly straight line. You change between moving sideways or even slightly backwards to find an easier or faster path that you can tackle, and then tackling that path. Scaling software is somewhat similar. You have to work within your budget or other constraints, and sometimes you have to move sideways by restructuring something. But when you climb a mountain, you climb it for the sheer challenge, because it's there. When you scale your infrastructure, you will have a business reason. Our business reason was to make our functional tests automated testing of the real application against a copy of the production server to be as useful to our development team as their unit tests. Now, the kind of scaling that makes everyone happiest because it's nearly free is finding ways to make more efficient use of existing resources. Because let's face it, nobody is going to give you more servers while your existing systems are wasting effort. We needed to run our tests faster than 4 hours, and there were things we could do even without buying more machines. One of the first things I noticed when I joined Badoo was that all of our tests went through the login screen. Each one spent 20 seconds deleting any previous username, typing the new username and the password, hitting the login button, and waiting for the server to authenticate and the appearance of the main screen, and only then navigating to what they wanted to test. I found out that we already had application support for deep links, URLs sent by email that would authenticate the user and take them to a particular part of the application. So I asked the server team to change what they sent back when we requested a test user. In addition to the password, they should also return an authentication token. So I made all the tests, except the ones actually testing login, use that to launch directly into the app. And that knocked 20 seconds off nearly all 300 tests and took the Android test time from 4 hours to about 3.5. The efficiency here is to avoid testing unrelated functionality in your tests. Take selective advantage of your direct access to the server to do the sort of very frequent setup, authentication, and so on that you need to do, while being careful to use the same API layers as the application to minimize drift, which might happen if, for instance, you try to access the database directly. When you access the server this way, make sure you keep 1 or 2 tests that are doing things the long way, actually friending someone through the app, and then in the same test, making sure that shouts reach them, because there's a danger you'll end up testing your test setup logic and drift away from what the application is doing. So Replacing login with token-based authentication was one of the first non-hardware efficiencies we made. Another efficiency we've achieved without new servers was done much more recently. When you build a project in C or Java, the build system will only recompile those parts which have changed, recompiling .o files and relinking libraries, and you can often arrange that test units will only run for affected source code. In contrast, functional tests usually do a full test run because the link between code and tests is tricky to make. For a couple of our builds, we now have logic that tries to do that change-based analysis. For application developers, the source code is already organized in directories or modules. These modules are listed by name in a manually maintained mapping file, and a developer and test engineer have associated each application module with one or more groups of tests. So changes in this file, in the chat module, will trigger all of the chat tests and all of the notification tests. Of course, some modules affect lots of the app, and some tests can be affected by many parts of the app. And all of this can change as the application changes. So the mapping is not simple, and unfortunately, it needs to be updated by hand. But even so, we achieve a useful reduction in test load. For automation engineers writing functional test code, things are a bit different. Our functional tests are written in Gherkin. I imagine most of you have seen given, when, then scripts. The given steps set things up for the test. Hang on. The given things set things up for the test. The first line makes the system contact the backend server and ask it for a new test user called James with 100 credits. The second given line makes sure the application is launched and that James is authenticated. This is where it used to type the username and password. Now, as I said, it just launches with an authentication token and waits for the landing screen to appear. The when step takes the app from the landing screen to the purchase page and then scrolls or presses buttons to buy a thing. And the then step verify that James has his thing and he has 80 credits remaining. Now, if a test engineer changes this test script, perhaps buying two things or adding a check for an emailed receipt, then clearly this script needs to be rerun. But in addition, if an engineer has changed how a step is implemented, we need to run all affected tests. This code is only for illustration, but since people like reading things, this is the step as it appears in the test script, and this is the regular expression that matches it. Here's the code that runs as a result, with the lines obtaining an object, representing the screen we want to work with, looking for something on that screen, and then doing something that will involve pressing buttons on the device. We can easily recognize changes in a step definition or template, like in this made-up example. So we would rerun any tests using this step. But it's not so easy to track down all the tests that will be affected if, for example, the purchase screen class that it relies on changed. So currently, we only rerun tests which have been affected directly or tests using step definitions which have changed. Any changes outside those two groups cause all tests to run. At some point, we intend to move to code coverage, recording coverage as each individual test runs, both at the application code level and at the functional test code level, and selecting tests whose coverage reports coincide with changes in code, at the application level for developers and at the functional test code level for test engineers. For the application code coverage, we will only consider application coverage collected during the when steps, because when steps mark what we're actually testing in the application. We may need to restructure some of our when steps to make sure that that is true, particularly any that make the server do things instead of tapping on the phone. They will need to wait for the application code to notice if they don't already. For the functional test code itself, we will use the coverage captured for all steps, given when and then, and perhaps also for some of the setup and teardown where that's relevant. We may be able to reduce the list of tests further for both sets of coverage because it will be so detailed. some particular sorts of changes, like code for authentication or the user's profile screen, might redundantly trigger many tests. So one approximation we could use would be to take each test in turn and only run it if its coverage mentions at least one of the changed lines that hasn't already been tested some number of times. Of course, the coverage data will be historical until the test is run, but it may still be a useful heuristic. So much for saving money. Now to stuff about phones. Another thing I encountered when I first joined Badoo was that we kept all our automation phones in this old, locked, glass-fronted cupboard, and it was annoying to have to walk all the way there, unlock the door, squint at the serial numbers to find the right phone, tap its unlock code just to dismiss a system dialog or to re-enable Wi-Fi. It was even worse when we moved to the ground floor because the phones stayed on the top floor. The cupboard was built into the wall and they didn't let us take the wall with us. We have a shiny new glass-fronted cupboard now, one with slots in all the sides so the phones don't overheat in summer, inner hot doors with holes for the phones to reach the USB hubs in badly drawn wire baskets on the back. Yeah, those are wire baskets. But sorry, we don't have a photo because of COVID-19. Oh, we sticky taped thin super magnets to the phones too, to hold them onto the doors. And if they still insisted on sliding down, we put cube magnets underneath them, but not near the sensor by the USB socket that makes the screen turn off. We don't plan to scale beyond a few dozen phones. Imagine how unmaintainable hundreds of phones would be. We have scaled to hundreds of emulators though. Anyway, when I was working at Shazam, the phones were actually in a locked cupboard in the machine room, down a long corridor. So I'd already written a simple ADB-based web script that runs on the machine hosting the phones. Since I'd uploaded my solution to GitHub, I was able to deploy it at Badoo too, with some extra tweaks for our setup. It's called CGI ADB Remote, and the proper link will show up shortly. The homepage shows all the phones and emulators for all the ADB instances it can find running on the host. Clicking on the device link lets you interact with the screen, and clicking on the FS links let you browse the file system. The file screen lets you explore the directories and download files from the phone to the browser by clicking on the links. And it can also exploit SU if you need to access secure files and your device is rooted. Most emulators are rooted unless they have the Play Store app, but there's no provision here for file upload. In screen mode, you can see the phone or emulator screen in your browser on the right here, and you can tap or drag on it with whatever you're pretending is your finger. In the left panel, there are various device controls, so hardware buttons, keyboard input, and so on. It can auto-scale the device screen, so even high-resolution displays fit within the browser window, but you can turn that off. One thing you'll probably want to change. The default screen refresh rate is once every several seconds, because I haven't changed it since I wrote it at Shazam, when we were worried that taking it and sending screenshots too often on older phones would upset our tests. Excuse me. So these days, once or twice a second is probably fine. Sorry, I've got something in my eye. I should mention Smartphone Test Farm at this point. It's a scalable open source lending library for your own phones, letting your developers virtually or physically borrow them and access them remotely through ADB, and much like CGI ADB Remote, through the browser. But it has a much slicker interface. The drawback is that it only works with phones, and when I checked last, they had no plans to support emulators. CGI ADB Remote, and there's the link I promised, supports both phones and emulators. The Chrome browser also has a nice plugin for Android device access, but it's not quite appropriate for our scaling. So, a word about hardware for phones. We've struggled to find reliable USB hardware. The phones keep disappearing from the computer, and though they're not moving and nobody is touching them, we suspect electrical noise from the air conditioner or other sources, even with shielded cables. My preference in hubs is to avoid anything with built-in cleverness or automatic switching. I find clever equipment tends to argue with other clever equipment. I've even had hubs which refused to recognize other hubs of exactly the same model. So I go for USB 2 everywhere with the surprisingly reliable Amazon Basics 4-port mini hubs plugged together. For power, we use these V-shaped cables, sometimes called Y cables, and anchor power blocks. At some point, we're planning to explore 3D printed fake batteries with a wired power supply to avoid the whole exploding batteries thing. These 10-meter extender cables connect the host machines in the machine room to the phone cupboard several meters away on the nearest usefully available wall, so we can get to them without bothering ops. Last thing about hardware, though not really about hardware. We bought a new group of phones to test on, and the automated tests install failed every time the test run started, but not when plugged into my laptop. To cut a long and frustrating story short, the Samsung A40 briefly disconnects its USB bus about 20 seconds after you unlock the screen the first time after a reboot, which reliably coincided with when our automated tests were trying to install, after automatically rebooting and unlocking the phones. So expect the unexpected. Anyway, in our cupboard were 4 different models of Android phone, each plugged into one of 4 TeamCity test agents running on 4 Mac Minis. TeamCity is a commercial continuous integration or CI system, much like Jenkins. You submit test jobs to a central server and it makes the other machines, called agents, run them. Test results are then published by the server. The trouble was that we now needed these Mac Minis to run iOS simulators for iOS testing, so we had to move the test agents. This gave us a great excuse to move Android tests to much more cost-effective hardware, and in particular into 4 Docker containers on one new Linux host. In case anyone isn't clear on Docker, it's a system that lets you create and share software bundles, typically Linux-based, and then efficiently run them against the host's own kernel, but isolated in their own sandboxed network, disk, and process tree, and I'll go into more detail about it later. Porting the software side of our test system was a simple first step to running against emulators on Linux, which was our ultimate goal. But the hardware was a problem. All the phones were moving from 4 Mac Mini USB networks to one Linux USB network. In principle, we could have had all the agents share one instance of ADB and given each agent a list of all the Android devices of the appropriate model. But as I've mentioned, we had this problem that the phones tended to disappear from the USB network. We'd found that stopping and restarting the Adb server at the start of each test run was somewhat helpful in preventing that for the rest of the run. But obviously, if the agents are sharing the Adb server, resetting it for one would interfere with any ongoing tests on the other agents. Now, the plan was to give one USB bus to each Docker container using bind mounts. But with initial trials, where I only had one agent set up in Docker, I found that the phones disappeared from Docker within minutes, even though they were still visible if I ran ADB directly on the main Linux machine. It turned out that the phones were frequently dropping off USB and reconnecting very quickly. It was only for fractions of a second, but it was enough. This command shows the special nodes or device files representing the USB devices. So if you, or the air conditioning electrical noise, unplugs this 014 device from the computer, however briefly, this 014 node vanishes. And if that same device comes back, even though it was originally 014, it would get the next unused number, 015, 016, and so on. Now, with a very brief disappearance under Linux and macOS and Windows, ADB re-registers the phone quickly, and normally nobody notices. But the way Docker containers work, although the device files vanish inside the container when the device disappears, the new device files created by Linux after the container starts wouldn't appear inside the container. ADB would never see the new 015 node, so the phones never came back. We tried monitoring for these changes outside the container and creating the new nodes inside the container, we told the udev system to run docker exec mcnod. But although they had the right major and minor numbers, they were not functional. What made these new device nodes visible and usable was running the container with the privileged flag. This simply gives containers live and direct access to the host's version of the entire /dev directory, complete with the new device file names each time the phone's reconnected. Now, although using privileged mode allowed ADB to hide the phone's brief disconnection, it meant I couldn't use bind mounts to restrict each container to a particular USB bus. So each of the ADB agents would see all of the phones and they would have a fight over who could claim the fastest. When ADB starts up, and periodically after startup, it recursively scans all the USB device nodes under DevBus USB to find things that look like phones. It contacts the process on each phone to ask for the phone's unique ID in blue here, and if it receives one from the phone, it holds that node open so no other process can talk with that phone. It also maintains a mapping between the ID and the device node, so that you don't have to, and you don't have to worry about USB file mappings. If the phone is unplugged or is interrupted by the air conditioning's electrical noise, the node is closed and deleted, and ADB updates its mapping. If a phone appears, ADB opens and registers that node, assuming it gets to it before anyone else. So to stop the different agents' ADB instances from trying to claim all the phones, I patched in an environment variable to restrict each one to a particular USB bus. And that was quite easy to add to ADB. Where things became more involved was when we added a fifth agent for Motorola phones because we'd run out of USB buses on the host. So here's a third way to list USB devices. You can see how it makes explicit the red USB bus and green device green device serial numbers in the listing from the other slides. I'll point out this purple USB device ID there. All USB devices have these. The first half is the vendor ID. All devices with VID of 18D1 are made by Motorola. The second half is the product ID, a number each manufacturer allocates for all devices marked with their VID. And Motorola decided that for them, 4E42 refers to the Razer Nexus 7. Now, this unique device model ID, the USB VidPID, is part of the low-level USB protocol and is available to ADB without claiming exclusive access to the device file. So two ADB instances which are able to see the same phone don't have to fight or coordinate to test it. So I made two agents share one USB bus and patched in a new environment variable specifying the device model VidPIDs that each instance of ADB should register. So that's how I segregated several groups of phones to different Docker containers and moved our CI agents off Mac Minis and onto Linux. This is a snippet of the patch, but don't bother reading it. It's only a small part of it. The URL to the article I wrote about this is unfortunately very long, so there's a tiny URL for it as well. Links will also be on a slide at the end. I never offered this patch to the Android project. It seemed a bit too specialized, but having had a later patch accepted, maybe I'll give it a go. So now I've shown you a patch to ADB, I bet you're all excited to try hacking on it for yourselves. It's written in C, so you need to know that. And I'm going to present the cheat sheet I put together for myself from the Android developer website on how to build ADB. The main reference, of course, is the official developer setup page from the top link here. And it explains how to download the Android source, which is arranged in lots of Git repositories, all managed by the repo command. In principle, you could just download a subset of it, but they didn't have notes about that when I did it, and I'm pretty sure they haven't written any since, because most people downloading Android want to build Android, not just the tools. If you're just patching the latest release, you can use master, but if you need a different version, you can list the branches with this git command here in the repo manifests git. We're still using v3.9 of ADB, which is roughly Oreo, because when I tried to move to v4.1, it started complaining about duplicate devices, and I haven't had time to get to the bottom of why. v39 has a very strange relationship with Java, which is why I'm clearing the Java home here before changing my branch there. To set up the general environment, you use this source command, and then you use this launch command to say which platform you're targeting. The ADB code lives in system core ADB, and obviously you edit the code before building. It makes it pretty simple for recent branches, but for v39, you have to both ensure that Java is on your path and say that you're not using it. The build results are put into this directory down here. The most annoying problem I had with building Android was the occasional failure from a special part of the build system called Ninja. Make Clean did not fix it, and the only workaround I had when it occurred was to commit my work, change to a completely different branch, try to build, and then switch back again. As I say here, head was sometimes broken for Oreo, but these days they're pretty good at keeping head working. Submitting to ADB is easy. You commit to Git as usual, and then run repo upload to send those changes to Google. Repo adds and maintains a unique ID in the Git comments, so updates on your branch are usefully grouped to the same patch review webpage. The code review happens on the website, and you just do more Git upload and repo submits to submit changes. So, now we have shiny new ADB executables with extra environment variables. The next ADB patch I had to write happened because I tried to run emulators in Docker. Our Linux server with the phones was half idle. The phones don't take up much CPU for testing, and we had plenty of power to explore emulators. At the time, the emulator snapshot system was not reliable for us, and since booting Android takes a while, I wanted a solution that kept the emulators running all the time, essentially handling them like a cupboard of phones. Since I wasn't particularly familiar with Docker, and we had the idea it would be pretty to be able to see all the emulators working on a display, much like the phones in their cupboard, I cooked up a system that would manage 16 emulators running under XVFB inside one container, and we were going to use VNC to watch it from the outside. The control script first needed to clone the base AVD, because this was before the emulator's new read-only flag. And it made sure that there were only 3 emulators booting at a time, because booting all the emulators at once made the server very unhappy. Once the emulators were up, the script checked every minute so that it could talk to each package manager in turn, and it restarted any emulator which failed, just like a phone which crashed or ran out of battery. Unfortunately, we gave up on the pretty display and made the emulators headless because it wasted too much compute power. The emulator cupboard worked well for our main application, but our newer product was back then using a library that sadly used the device's International Mobile Equipment Identity, IMEI, as a unique application user ID. Now, we stopped using that library a good while ago, but in case you find yourself using something which has made the same mistake, I'll share my horrible solution. The IMEI can't be used as a unique ID, not only because it exists on devices with a SIM card, not tablets, but because various no-name manufacturers have given all their phones the same unique number. The SDK binary has a constant string for the IMEI, so it's the same on all emulators too. The easiest solution was to make the control script clone the SDK with one tree for each AVD clone, and then byte edit copies of the emulator as shown on the slide. Hopefully none of you will ever need this, but it's here just in case. I would have patched the emulator to take an environment variable, but frankly building the emulator seemed like too much work and somewhat risky in case my setup was subtly wrong. Our emulator cupboard did so well that we bought 2 new servers and spun up 2 new agents, but we found that although they had 28 cores and could run 28 emulators, ADB didn't work properly with more than 16, and astonishingly, emulators would also vanish, much like phones. For various reasons, running 2 emulator cupboards side by side did not work, so I was forced to patch ADB again, this time to set the emulator limit from an environment variable. It turns out that ADB used to be able to handle more emulators, but Android Wear watches started using emulator 17's port in their documentation, so they added this limit to prevent those different uses from clashing. Now, changing the limit to an environment variable was an easy change, but it sparked an unexpectedly long discussion in Google's code review. Although the patch has now been accepted into v4.1, the default remains 16, in case that's something you run into. Now, don't read this. Again, there's more to the patch on the code review website and nearly a month of discussion for a simple patch. I dread to imagine how much discussion the vidpid USB bus patch would cause. So having solved that issue, we faced new demands and new problems. We were running happily on our new servers with the permanently booted emulators in their virtual cupboard when we got a new requirement. Various departments started asking for automatic walkthroughs of the application. The translation people wanted to see all the strings on all the screens. The product owners wanted to be able to storyboard the application and move screens around. Design wanted to see how screens looked on different sized devices. We wrote a system called Live Shots to run special tests that walked through the application, taking screenshots at various points, with one test run for each requested screen geometry, and a website and a database to show and compare them. There's a link at the end of the talk. There's a link at the end to a talk in Russian. To support these screen geometries, I considered making the cupboard of emulators stop and restart with new AVDs for each run, but we were also beginning to try to write tests for the chat system, which needed 2 devices each, and by then the emulator snapshot system had become more reliable, so I decided to try snapshots. I created a new Docker container for this, but I based it on a little web server I had previously added to the cupboard of emulators to help with monitoring and controls. I added an extra endpoint to let a client remotely start and stop containers running different AVD snapshots on demand. It was useful to steal the control system from the emulator cupboard because it preserved the control and monitoring logic we were already using. Now, we also wanted test run agents to be able to run against emulators on other hosts, not just emulators on the same machine. So I made ADB visible on all network interfaces, not just localhost, with the -A option. And for safety, I put it in a loop like this. Using the no daemon directive means it will block the loop unless something goes wrong. And on error, the loop uses ADB kill server to take down any imposters and then runs again. And I'm not showing the control logic that tries to handle a runaway failure if the required port becomes blocked or the executable becomes corrupt or whatever. But just imagine there's something amazing there. One particularly nice aspect of this was that the system operated much like a vending machine. Developers could now ask for an emulator just like the automated tests we're using, and even request one from in the US or in Europe for regional server differences instead of a UK-based one. I nicknamed the system Ticket Machine, and it worked nicely both for developers and the test runs, so we shifted pretty seamlessly from the permanently running emulators to emulators started on demand. So here are a couple of examples of requests for the Ticket Machine web server. This top one requests an emulator specifying the part of the Docker image name. It can take various other options to tweak the config ini within the AVD or to boot without the snapshot. In the response, the red text gives the parameters that ADB needs to talk to the emulator from your local machine, and this blue text is the identifier you use to shut the emulator down again. The response is in plain text to make it easy for humans to copy and paste into commands, but it's also easy for computers to parse. The bottom panel is an example of the part of the API brought forward from the emulator cupboard. I made the low-level QEMU emulator commands available as HTTP requests, which was much easier for our use case than faking a console-based approach. If you're not aware of the stuff that you can ask QEMU to do to your running Android emulator, I encourage you to try Telnet localhost 5554 next time you have an emulator running. The help command has extra help on each command if you type help AVD or whatever. Things like fold should be useful with the new flexible displays if you have particular behaviors you want to test, and finger or fingerprint might also be handy, although you can of course stub some things out in your tests by other means if you want. Oh, a little tip. If you clear the emulator console auth token file on the machine running the emulator, the QEMU interface won't demand a password from you. Now, we wanted to keep using our existing AVDs when we moved to the fast snapshot startup in the ticket machine, but the application walkthroughs meant that people wanted a snapshot for each AVD multiplied by each screen geometry, and then baking those into Docker images and tagging them. And all this was boring and error-prone by hand, so I scripted it. There were 3 parts to scripting these builds. Firstly, writing a wrapper script to loop through each screen geometry and invoke the build, optionally allow me to sanity test each new snapshot manually, and then push it to our Docker repo for general use. Secondly, a script to build a Docker image and implement the workaround to give the special kernel access that isn't available when using the normal Docker build system. And finally, inside the container, automating the various first-time operations that needed to be run for each new snapshot, dismissing Chrome, camera dialogues, and so on. I'll cover these last 2. To explain the build with kernel access workaround, I'm going to outline briefly how Docker works, and then how building Docker images happen. By the way, it's an unfortunate clash of vocabulary that the term image is used in both by Docker and within Android AVDs, so I may refer to Docker images as containers when I'm talking about both, and hopefully that won't be confusing. So Docker images are things that contain small but complete Unix file systems, etc., bin, temp, and so on. But Docker kind of makes them behave like executables. When you run a normal binary executable, the system loads it into RAM and runs it. Similarly, when you ask Docker to run an image, Docker uses an overlay file system to make what looks like a copy of the image's file system. I previously mentioned that each Docker container has its own process tree, its own network, and its own filing system. This copy, this overlay, is its filing system. In that container, Docker runs whatever command you've specified should be run in the image configuration. If that command changes, deletes, or creates files, those changes are put in the overlay, not in the original image. When that command exits, Docker keeps a reference to the changes caused by the command, together with a reference to the original image. The container is normally discarded, it's just the remains of some service. But if you want to keep the new state, it can be committed into Docker and tagged with an identifier, just like a git commit, to turn the container into a new image incorporating these new changes. And this new image can then be run by Docker just like any other. So far, so good. Now, how do I build my own images in Docker? Docker images are built using a plain text script. The first line specifies a starting image. It could be one you've made yourself, but this from line asks for a basic Ubuntu system which someone out there on the internet has built for everyone and has registered at a well-trusted location. Docker images have a hexagibberish identifier, much like git commits have, and can be tagged with human-friendly names in the same way. Each subsequent line in the build script can create a new container based on the image created by the previous line and runs whatever command is given, creating the next new image. So this first run line is a composite shell command that downloads the latest module version database with this apt update and installs a list of modules required by the Android SDK. Let's pretend there's a real list of modules here. Now this last apt clean bit isn't strictly necessary. It removes the module list database because we won't use it again. And most people want to keep their Docker images as small as possible for speedy redeployment on lots of servers. So they use Alpine Linux instead of Ubuntu as a base, and will delete any files they don't eventually need for their running system. But we don't update these containers often, and we find it handy to keep a fuller set of tools available in case we need to go inside a running container to find out quickly what the emulator is doing. So we use Ubuntu and we don't tidy up. So given that run command, we now have an image of the basic Ubuntu system with several modules needed by the Android emulator added on top. This copy line copies the various files into the container from the directory relative to the build script. We can pretend that this copies the Android SDK's emulator and perhaps the AVD we need to snapshot. The entry point line sets up a command that should be run by default when the container is started, and the image created by the last line is the result of the overall build. So that's how Docker builds happen. Remember, I'm trying to write a script that builds a Docker image with an Android emulator snapshot, so it starts up in 4 seconds rather than taking 30 seconds to boot. The problem I had was that when I needed to run the emulator to cancel all the first-time dialogues and then create a snapshot to be cooked into the image, but until Docker 1903, you were not able to run the emulator inside the Docker build command because the emulator needs special kernel support. In Docker 1903, they added Docker build x build allow security and secure. But back then, I had to use the normal build system as far as I could and then mimic what the build script does, which is to run my command inside an image, but in this case, run it with these special kernel privileges, this privilege flag, and then commit the changes. Having worked that out, I just needed to write a script for inside the container that booted the emulator, waited for the boot to finish, and then terminated the emulator to create the snapshot before shutting the container down. The wrapper script then committed the container with the new snapshot in it to Docker. Easy peasy. Originally, I used AVDs from the emulator cupboard with all the first-time dialogues, allow camera to see your location, already dismissed, by hand. But now the script created the AVDs using AVD Manager, and these AVDs needed automation to dismiss the first-time use dialogues on first run, because it's more consistent than finding the hidden properties with each new release. Spinning up Appium inside the container seemed like massive overkill, because I only wanted to press a few buttons, and I knew I could do that with ADB shell input, ADB shell UI automator dump, and so on. So I ended up with some shell functions to do that, which are available in the gist mentioned at the top of this slide if you're interested. The functions let you wait for and press on buttons by name. They let you wait for things to appear on the screen by ID, and press on things that are only pretending to be buttons. The standard sort of coordinate manipulation stuff. The motivation for automating all of this snapshot container generation was that we were upgrading from Marshmallow to Pi, and I didn't want to go through creating all the different screen dimensions again. As part of this, I found we also had to upgrade the emulator executable. Android Pi required a newer emulated hardware layer called Ranchu. The older one was called Goldfish. Unfortunately, we encountered a memory leak in the new emulator's OpenGL layer. Presumably our tests were being particularly hard on the emulator, or maybe we were unusual in keeping emulators running between tests. Anyhow, Google were interested that we were triggering a leak and gave us a custom emulator build that fixed it, but that emulator build unfortunately had a different bug. Every few seconds, the emulator ran ADB, and while those ADB commands terminated normally, the emulator was never checking for the exit code, creating what many of you will know is called a zombie process. These exit codes stay in the process table until they're checked, but the emulator wasn't checking them, so more and more of the process table was taken up with zombies until the table was full and the machine couldn't start any new processes to operate. Neither Google nor we were clear why it was happening, but we needed that version of the emulator with its graphics fix. So my workaround was to fork Linux Inject, which is a project that makes it easy to inject a library into a running process. So you can see the URLs here on the slide. It needs ptrace, which needs special kernel access, but the Docker container was already running with the privileged flag for the VMX support required by the emulator, so that wasn't a problem. My library created a thread at load time which scanned the prop directory every 20 seconds to monitor the process list and to reap any zombies which were older. It wasn't elegant, but it kept the problem under control until the graphics fixes made it into the mainstream emulator and we could shift to that. There are a couple of more small solutions to end this section, and here's the first. Around 2018, Google decided that APK files were becoming too big and introduced the Android application bundle, so Play Store could deliver only the parts of an application that any particular phone needed, so 1 or 2 languages, 1 screen density, and the core functionality itself. And as part of this, they introduced the related APKs format. And after a few months, our development team asked us to use that directly, since that was the real environment. But I found that Bundle Tool, the tool that lets you install APKs file, couldn't talk to remote emulators. I considered using something to make the remote server look like it was running locally, the standard Unix SOCAT utility, or the ADB port forward server mentioned here, but I decided it would be better to try to fix the tool properly. While I was looking at it, I discovered that DDMlib, the embedded ADB client library, had partial support for remote servers and only needed 1 file tweaking. I couldn't work out how to submit that to DDMlib, so I submitted it as a patch, as this patch, to Bundle Tool, so that it was at least somewhere where somebody in need might find it. I still don't know how to submit to DDMlib, so if any of you know, please grab me after the talk. So this next is, I think, the smallest ADB-related patch I'll mention. Our ADB servers can't just be the default ones. They need vidpid filtering on them, or a fixed emulator count, or libUSB disabled, or a particular network port. And if for some reason that special ADB server is killed, something runs ADB at the wrong time and in the wrong context, from the machine monitoring, from CGI ADB remote, from the command line, or something else, then the default ADB client will try to start its own ADB server, which won't have the special environment variables, and will then be able to see the whole machine, claim all of the hardware, and confuse all of the emulators. It really messes things up. So this trivial patch simply prevents the ADB client from trying to start a server if it doesn't already exist. I hope to develop something similar to prevent an ADB client from killing a server on version mismatch, which happens to us from time to time, since we're still on v3.9, as I've mentioned, and developers are usually on v4.1. So no more patches. Now, emulators in Docker are good, but more emulators are better, and for that we need more hardware. So here's something about choosing and scaling servers. I mentioned that our first servers could run 28 emulators some while ago, and we were lucky with our first 2 sets of servers. We happened to choose CPUs which ran 1 emulator for each non-hyper-threaded core. But more recently we bought CPUs with 32 cores and were surprised when tests were no faster on 32 emulators than if we only configured 20. And then we noticed they only had 20 megabytes of level 3 cache. So now we choose servers based on each emulator needing 1 core, 2 megabytes of level 3 cache, and 2 to 3 gigabytes of RAM, depending on the AVD's RAM setting. I always find it slightly confusing that we have 2 CPUs in all our servers, but that the statistics are quoted in terms of 1 CPU, so be careful if you're reading the output of the lscpu command in Linux. Just lately, we've had a flurry of borrowing and being given spare CPU capacity from other departments, and having had more CPUs to try out, it now seems that each emulator also needs 2000 CPU marks, a power rating I found on cpubenchmark.net. Oh, and we like SSDs much more than hard disks. Now, Intel CPUs generally seem to have a poorer core to level 3 ratio than AMD chips, and the few AMD processors we've tried, particularly the EPYC range, have a much better and more consistent core to cache ratio, and they seem to be much more responsive on the command line, even when they're running emulators flat out. With emulator snapshots, If you change an ini file in the AVD or upgrade the Android SDK binary, the emulator will notice the incompatible change and will treat the snapshot as if it were corrupt. It will do a full normal boot. But if you have Android AVDs with Intel snapshots in your Docker containers and run them on AMD, or try to run AMD snapshots on Intel, the emulator will not flag the change. It will start up, but the emulated device will be broken. So you will need to run them with the emulator option no snapshot load, and potentially recreate the snapshot for the new architecture and commit the Docker image so that you have it available. Once you've bought a new server, how many emulators can you run on it? Well, my process is pretty simple. I use the core count, the level 3 cache, the RAM size, the CPU mark parameters to make a first guess. They all impose an upper bound, so I choose the smallest and kick off tests to see how well they go. I try running with 10% with the guess, with 10% more and 10% fewer, and then 20% more or fewer, trying to find the fastest run. And obviously I could optimize this by running different numbers of emulators on each server during a single test run, but it's easier to schedule a few runs on the CI, each with different emulator counts, and then leave it alone for a few hours while I get on with something else. What I normally see is a 1/x curve on one side of the graph, where the cumulative test time is divided by the number of emulators, leading to a dip and a gradual incline on the other side, where emulators start fighting over resources like CPU time. If my first guess and the 10% runs on either side don't show much difference, I assume I'm in the slow incline part and try again with fewer emulators. If there's a big difference, I'm in the 1/x part and I need to try more emulators. Of course, it's not just about test speed. We also need to check that the number of failed tests is consistent with the expected results, and normally failures start increasing at the far right of the graph. I don't actually draw a graph like that, though. I look at the machine stats. So the 3 lumps in each of these graphs are the 3 test runs, with the base guessed first, 10% more emulators in the middle, and 10% fewer emulators at the end. The RAM graph is comfortably boring. We're well within capacity, and unsurprisingly, more emulators use more RAM than fewer emulators. Obviously, I read the elapsed wall clock time from the test run logs and not from these graphs, but these equal-sized arrows show that the 10% more emulators test run is slightly slower than the other two, which means that the emulator count estimate was good and we're near the sweet spot. I would schedule a run with 20% fewer emulators to see whether that's even faster. The I/O wait graph is comfortable too. These spikes show the emulators all booting from snapshot, but once they've booted, everything is in RAM and it all goes quiet. If this were too high, then the emulators would be being held up by accessing the disks. We could try swapping the hard drives for SSDs, or increasing RAM for cache, or using a TempFS overlay, which we now do for iOS simulators. Obviously, whenever you change some hardware or system parameter, you'll need to rerun the emulator calibration again and see how it goes. The CPU load graph shows that the CPU is the only bottleneck, which means that once we find a comfortable level here, we can't do any better. The emulators are simply using all the compute power of the machine. The red line is for the number of CPU threads, 32, but the emulator seems to have a strange relationship with hyperthreading, and the core count is only 16, the purple line on this machine. If you remember, I earlier mentioned that I only boot 3 at a time to spread the load. That avoids these initial spikes being 10 times worse. Another CPU graph, and again, 100% level is at the top, seems to relate to the CPU thread count, so I'm more interested at the 50% line halfway up. Until recently, we'd never seen a network problem while calibrating, except while I accidentally tested servers in the wrong continent and made the network people very grumpy. But just recently, some new servers in the US completed the tests in good time, but the overall Team City job took 10 to 15 minutes longer than expected to complete, and we found that that was the time taken to transfer our excessively large log files over. We fixed that by compressing them and reducing the default logging level. Now, As you buy more and more servers, the sheer amount of computing resources becomes something to handle in its own right, which leads to this final chunk of the talk, our current experiments and future plans. While Docker is great for packaging up software with all its requirements and helpful for plugging together servers that need to talk to each other, and although you can connect remotely to Docker from other hosts to start containers, it tends to need scripting. And this is fine if you have a simple or relatively stable setup, but these days people don't want to mess with handling lots of servers individually. They want to be able to tell the computer, run 50 of these servers, or demand is rising, add 10 more of those to the load balancer magic, without being bothered about exactly which machines they run on. It's all commodity, and that is the promise of Kubernetes. If you're unfamiliar with Kubernetes, it's like Docker distributed over several machines and operated through declarative configuration files. Now, I'm in a bit of a love-hate state with Kubernetes. I love the declarative style and how easy it is to make a lot of service setup for the normal sorts of load balance services that many companies, including ourselves, run. But it feels awkward and unnatural for this emulators on demand system. So either I'm doing it wrong or it's the wrong tool for the job. And it's also been opaque when things have gone wrong. Sometimes a deployment that usually starts in a few seconds will exceed 5 minutes, but Kubernetes truncates the logs to the first few lines, not the final few lines. So working out what was going on became much harder. Since it seems that we, along with many others, will migrate to Kubernetes, we have to try to fit this weird emulators on demand system into it. So here's my prototype. Essentially, I just treat it like Docker. Whichever CI agent is running asks Kubernetes for a list of nodes marked with that agent's name. We need to know how many emulators to run, and Kubernetes can provide the core count as part of that query, but it doesn't know the level 3 cache size, so we have to run a service on each of the nodes to make those queries. Having obtained the level 3 value, the agent can now work out how many emulators each node can run, so we move to the next stage. Oh, except that now I've also found the CPU mark parameter is useful. I'll need to retrieve the CPU node's CPU model while I'm getting the level 3 cache size and check in a CPU mark lookup table. Anyway, to the next stage. So the agent now constructs and runs a deployment configuration with a modified version of the on-demand emulators server, now only used to report status and host the Adb server loop, a CGI Adb remote from GitHub, and as many emulator containers as the node will support based on the core count, level 3 cache size, and so on. Our emulator containers notice they're running under Kubernetes and enter a waiting state where they use the status monitor to coordinate booting only 2 or 3 emulators at a time. The agent waits for all the nodes' deployments to return and works out the Adb server sockets and emulator manager sockets to pass to the rest of the test run. And as with the Docker solution, the test run often starts with some of the emulators not yet having booted, but it starts to use more of those emulators as they become ready. Now, this is fine as a proof of concept that we can use Kubernetes, but it doesn't really give us much benefit over Docker. Now that I know a bit more about Kubernetes, I can imagine how to move beyond the prototype and operate in a slightly more elegant way. I could use a Kubernetes custom resource to say how many emulators each node can run, perhaps avoiding explicitly mentioning nodes entirely. And I can make every emulator pod run its own ADB to completely eliminate trying to get them to share ADBs. And I could deploy a boot queuer to coordinate the boot 3 at a time logic on each host, and various other details that I haven't worked out. If any of you is a Kubernetes expert, I would love to chat afterwards. So, moving to our future. Regardless of Docker or Kubernetes, what we're really wasting resources in is in the way each of our agents currently has a fixed allocation of emulators. Once an agent has run out of tests or didn't have many in the first place, it can't release its emulators to the other agents who could be using them. This will be particularly annoying when our test selection logic has improved and made smaller test runs more common, and people are waiting 10 minutes to run a handful of tests despite lots of unused emulator capacity because the bottleneck has shifted and there are too few TeamCity agents. It's worth underlining that fixing one bottleneck in your system often causes new bottlenecks. Originally, we only ran full tests, and our bottleneck was unnecessary steps within our tests. Replacing login with authentication tokens improved the speed. Then our bottleneck was too few emulators, causing slow full test runs, so we got more emulators. Then our tests ran fast enough that developers with small code changes wanted to run them, and the bottleneck became running hundreds of unnecessary tests, so we've begun to select fewer tests based on source code changes. And soon our bottleneck will almost be the inverse of our first problem, lots of emulators standing idle. And then once we arrange to shift idle emulators between the agents, the bottleneck will be too few agents to use the spare emulators. It's like our architecture needs to be turned inside out every so often. So our next steps will probably be, firstly, to work out a system that tries to give spare emulator slots to agents that could be using them, and this should be fairly easy. Secondly, working out whether it's cheaper to pay for lots of TeamCity agent licenses, even though those agents will often stand idle, or to design something which operates like lots of agents, but ones we don't have to pay for. This last option has to keep working with our existing build and unit test system in TeamCity. It's quite a complicated task, so it gets the most complicated slide, and I break out my fake laser pointer again. We would probably use one TeamCity agent as a gateway, immediately sending each test job, binaries, test selection, and other config to a new server which queues and prioritizes the jobs based on trying to run smaller test sets quickly and trying not to leave the emulators idle, but trying not to live lock larger test sets forever because too many small jobs are sneaking in and eating the emulators. We already execute our test jobs in a Docker container separate from the TeamCity agent itself, so this could be a fairly incremental shift. The detailed test results, the low-level logs, may well be made available outside of TeamCity. We're looking into test run results handling projects already, but we would probably want at least the basic pass-fail details to be posted back to TeamCity to provide continuity for the rest of the company. And I have ideas for achieving this and handling job cancellation elegantly based on a secondary job, dependency tricks, and agent parameters. You can ask me afterwards if you're interested. So that's where we are now. We're higher up than we are, but we're still climbing our mountain. None of us has all the answers, and most of us are just banging the rocks together until something works. It always amazes me how far we've gone from a few phones plugged into a bunch of Mac Minis to over a dozen servers and several hundred emulators spread around the world. And the fact that we're now at a level where we've outgrown a commercial system like TeamCity and are considering how to schedule dynamic testing with allocation on a fleet of emulators, I find it amazing. I've covered a lot of stuff. The importance of working with what you already have while making testing more efficient, some tips on real phones, how I put phones and emulators into Docker and patched ADB to make that work, how to build ADB, scaling emulators on server hardware, some workarounds we needed when things went wrong, our experiment with Kubernetes, and what we're going to have to tackle in the fairly near future. My hope is that at least some of these things will be useful or thought-provoking to you. So thanks for coming, and thanks for staying to the end. I'll take questions next with a slide holding all the URLs from the talk in something like the order they appeared. But for this slide, I'll point out our GitHub and tech blog, which have interesting things on them. Any questions?
So, Tim, thanks for your talk. That was really nice and interesting. We have some questions in our Telegram chat, and well, actually, we have some questions from our host, and I think he can ask you directly, right? So, if you
sure.
include him.
Yep, that's fine.
Hi team, thank you for a great talk. Do you see, yes, IRQ project and Selenite also with Android integration? IRQ Selenite.
IR cubed. I'm not familiar with IR cubed, I'm afraid.
Okay, I see. It's no problem. So the second question is, it's really good for Android, but what are you think about iOS testing? Do you have experience with that, and how we can put our iOS infrastructure to Android and to Docker and Kubernetes?
Okay, so I don't believe you can put the iOS simulator into Docker, because my understanding is Docker only pretends to be Linux. What we currently use is a whole bunch of the Mac Pro, the things that look like dustbins.
Okay.
We have a whole bunch of those in a very air-conditioned room, and we basically just run a whole bucket load of simulators on them. We have a server that we have a server that tries to coordinate starting and stopping the simulators and making. I think we have something to make installing to the emulators more efficient. So we only have to send the application to the server, and then the server does the installation to the simulators. So it's a bit more efficient. But yeah, basically we have the same sort of system as this ticket machine, but it's a bit more advanced and very Mac specific. But no, it doesn't run in Docker. It just runs directly on the Mac operating system.
Mm-hmm. Okay, Tim, I have one more question. So actually imagine that there is a project and we only start having this issue with having many tests and running them for a long time, and we need to figure out how to start. So can you give some advice for such teams? So what will be your recipe, how to find these bottlenecks and where to start?
Logging. That's one of the things, actually, to be honest, we're not very good at. But basically, if you have to look at the graphs. I mean, most of the stuff that I do now for scaling in terms of bottlenecks, particularly, is looking at the graphs for the machines I showed you. We've solved a lot of the problems, but basically, you simply have, if you have a process that you think shouldn't be taking as long, you simply have to log it and look at the numbers. I don't know. I feel like you want me to give you sort of a magic wand and say, you just do this and suddenly it all works. But it really just comes down to looking at the numbers and run a single instance on your local machine, how fast that works, and then try to see why that maybe isn't applying at scale. Does that answer your question?
Okay, so that's fine for the answer. And maybe you can specify how much resources, hardware resources, do you use now for running your tests? I think you probably mentioned it in the beginning, but if you remember, then that's just interesting information for
we have
listeners.
I think it's about 50 server class machines, possibly a few more. It kind of changes depending on. We recently had a bit of upheaval with our servers. We were borrowing. We were borrowing space on unloaded servers that were used by a different department, and then that department was repurposed. So we lost all those machines, and we've had a big overhaul in which hardware. That's I mentioned in the talk. We've recently had lots and lots and lots of different CPUs to try. So I'm a little bit hazy on the exact numbers right now, but I think it's something around 50 server class machines.
Okay,
to be honest, I don't normally think about how many servers we have for Android emulators. Normally, I worry about how many Team City agents we have, which obviously isn't particularly important. So,
and
I think she's gone.
We have some connection problem. Okay.
She's in a quantum state.
Yes.
Yeah. So the question is, do you still use some real devices or use only emulators?
Yes, we still use real devices. That's why we have the new device cupboard, the badly drawn one. But we restrict the tests to the tests that we run on those are the tests that only work on the phones. So things like payments and I think it's mainly payments actually. We were doing some video related stuff on the phones as well, because that uses the video hardware, and obviously we need to make sure that real video hardware works. We're not very interested in how emulated video hardware works. So we do still have phones, a bunch of phones for testing, but most of our core testing is done on emulators.
Mm-hmm. Okay, thank you. That's interesting. And what about your team? So we talked about how much resources, how much tests do you have, but how many people you have to do all this stuff? So how many people support the infrastructure and how many people do the testing itself?
Sure. We have 3 people doing we have 3 people who are strictly doing the infrastructure. We have about 6 other people in the automation team who work on the sort of more of the test side of things, the espresso, for the page objects and all the various other things. But they will sometimes work on the infrastructure as well because it's interesting, and that's fine. And we have a whole bucket load of automation engineers who write the given when then scripts and debug them, and are beginning to also help to write the test steps and do more software related debugging. So yeah, it's
Mm-hmm.
I don't know, 24 people maybe.
Oh, wow, that's really huge team. And I suppose that it took also a long time to move from the old infrastructure to the new infrastructure. And how long was that actually?
Well, I've been at the company for 5 years, so kind of 5 years. But I mean, at each stage, we try. I try to keep the. I try to keep the steps invisible, essentially. I mean, testing is a bit like the sewer system. You only get complaints about it when it goes wrong. Usually nobody notices. So the fact that people generally haven't noticed what we're doing, apart from things have got faster. I mean, that's one of the notes I was going to put in the talk, but I cut it out because of time. Basically, obviously you have to log things in order to make sure that your system is working and it's scaled and all that sort of business. Sorry, I've got the thing not under the camera. There we go. That'll be a bit better. Where was I? Yes, sorry. So logging is obviously very important for making sure that the scaling and everything else is working, but it's also important because you have to keep historical data so that you know that it used to run. It used to take 2 hours to do something, and now it takes 10 minutes or something. And you can say, hey, look, we are actually earning our living. We're not just sitting on our backsides and browsing the internet all day. So it's important to have figures to show what you're doing.
Mm-hmm. And as I see from your speech, you also use lots of your own solutions made inside the Badoo. And do you take a look at external solutions, because time is running and the new solutions coming on the market? So how do you do this? So you prefer to keep your own solutions, or you monitor what new pops up and how to use it? So how do you deal with that?
It's a bit of both. So we don't we do monitor what's going on, but obviously we're busy with other things, so we can't spend all day on the internet just monitoring new developments. Typically what happens is when we have a when we have a new requirement or when something is going wrong, we'll do what I imagine most people do, which is to go and look and see if a solution already exists on the net. And if it doesn't, then we'll cook our own. But we do generally try to publish what we've done so that the next poor sod who comes along and has to solve the same problem will find a solution. I mean, that's partly, what I'm hoping this talk will do is to share some of that, some of those suggestions and some of those solutions.
Okay. So, Tim, it seems that we are done with all our questions. And thanks for your talk. That was really nice and interesting. And I hope our auditory can use it in their work and get some nice tips and tricks and find a way to apply it in their projects. So thank you very much. That was really nice. And if we also have our discussion zone available, so we will be happy to meet in discussion zone after this talk.
Yep.
Все верно. Thank you, Tim. Thank you for great talk.
Спасибо.